Hello, everyone. Welcome to the Audio Precision webinar. Today, Joe Bergin will be leading the conversation around headphone audio test, hearing aid audio test. And we'll be providing demonstrations in APX 500 software. My name is Paige, and as the producer of the event, I would like to go over a couple housekeeping items before we get started. So first, please note this session is being recorded. And when the webinar series concludes, I'll be sending out an email with a link so you can rewatch the webinar on your own time. Also, we welcome questions during the event. So if you have a question for Joe, please submit it via the chat function in Microsoft Teams. Joe has a lot of info to share with you today. So without further ado, Joe, I turn it over to you.
Great, thank you, Paige, and thanks to everyone for attending today. So before we get started, I just wanted to point out on most of the slides here, you'll see I have the Audio Precision logo and the Grass Sound and Vibration logo. As many of you know by now, we've kind of merged. We're both separate companies, but owned by the same parent company, and we have started to consolidate some of our functions. So those functions include technical support, which I'm a part of, sales and marketing. So I'm now part of a global technical support team. We have offices here in the USA, as well as in Europe, also in the UK, and a couple of offices in China as well. All right, we have a lot of material to cover, so I'm just going to jump right into it. First, we'll look at the agenda for today. So I'm going to have a very brief and a very simple introduction overview of hearing aids. And I wanted to mention, I have a fair bit of expertise in audio tests and audio analyzers, especially audio precision analyzers, but I am by no means an expert in hearing aids, and if that's what you're expecting today, you may be disappointed. So just to set the expectation. Next, we'll talk about the ANSI and IEC standards for hearing aid test. We'll review the test requirements in those standards. I'd like to talk about the test equipment required to conduct these tests. We'll do a demonstration, and finally we'll have some time for questions at the end, or as Paige mentioned, you're welcome to ask questions during the presentation. All right, so a little bit about hearing aids. These are marvelous little devices from an audio test perspective. They are both acoustic input and acoustic output, which is kind of unique from an audio test point of view. But they're also quite complex devices. So they all have typically a couple of microphones, or at least one, but quite often more than one. They have a power amplifier, a little loudspeaker called a receiver in the hearing aid industry, also called a receiver in telephony applications. They have a computer processor for digital signal processing. They're battery powered and have some controls, and they are in a tiny little package, really. This is a rather large behind the ear hearing aid that fits behind the outer ear. But as we'll see, there are some tiny ones that are completely hidden inside the ear canal. Now, in addition to these basic features, hearing aids have a lot of additional features, or they can have, such as noise reduction. They can have directional microphones to help the hearing aid determine the source of the incoming sound. They can have support for telecoils. So this is a magnetic coil that allows the audio to be transmitted via a loop around the building, or in some cases from a telephone receiver, so that the audio can be transmitted via magnetic field rather than acoustically through the air. Many of them have wireless connectivity. In earlier days, most of the hearing aid manufacturers had their own proprietary Bluetooth protocols for transmitting audio, and now the Bluetooth SIG has just come up with a standard for hearing aids that will allow all manufacturers to adopt the same standard, and I think we'll really see the Bluetooth take off from there. In addition, they can have remote controls. For example, you can control the programming and the features of the device from a smartphone, for example. Some have direct audio input, so a tiny little analog input jack that you can connect an external device to directly connect the audio to the hearing aid. Many have variable programming. The program that is processing the audio varies depending on the circumstance that the user is exposed to for better hearing, better listening conditions. And they can also have synchronization. So if you have, for example, two hearing aids, one for the left ear and one for the right ear, there can be communication between the two to optimize the acoustic experience for the listener, or for the user. Just a brief overview of the various styles of hearing aids. So we have on the left a behind the ear, as the name implies, the hearing aid fits behind the ear. A slightly smaller version of that, the mini behind the ear. And these have a hook called an ear hook, and typically you would attach a small piece of plastic tubing which would convey the sound from the receiver or loudspeaker inside the device into the ear, and there may be an ear mold inside to deliver the audio into the ear canal. Here we have a variation of the behind the ear called the receiver in canal. So in this case, the loudspeaker or the receiver is placed directly in the ear canal, and there's wires used to transmit the audio from the power amplifier inside the device into the receiver in the canal. Next over here we have an in the ear, and this looks a bit like the in the ear monitor that musicians use. So this one would have microphones on the outside, and then the sound is conveyed through the ear mold into the ear canal. So these sit in the outside of the ear canal. Smaller ones fit a little further in the canal, called the ITC, or in the canal. Then a smaller one yet is completely in the canal, this CIC. And finally on the right, the very tiniest one is an invisible in the canal, which is small enough to be inserted completely inside the ear canal and is totally invisible from outside. So you can't even tell that the person is wearing hearing aids. Now let's talk a bit about the hearing aid test standards. One of the main ones is the ANSI ASA-S 3.22. This was revised in 2014 last and reaffirmed in 2020. The title is Specification of Hearing Aid Characteristics, and this is widely used for production test of hearing aids. A similar standard from the international series IEC 60118. So 60118 is a multi-part series. I think there are 15 parts to the series. And this one, part 7, is titled Measurement of the Performance Characteristics of Hearing Aids for Production, Supply, and Delivery Quality Assurance Purposes. So this is very similar to the ANSI standard. The two are virtually identical, just a couple of different tests in one versus the other, but they are largely the same. We also have the part 0 of the IEC 60118 series, and this one is titled Measurement of the Performance Characteristics of Hearing Aids. This is used more for research and development. For example, if you were developing a new model of hearing aid and you wanted to develop a data sheet or specifications that you would deliver to a country that you're introducing the hearing aid to, you would more likely follow the tests in this standard. This covers a wider frequency range. I think it goes from 200 hertz to 8 kilohertz, whereas the production test standards cover 200 hertz to 5 kilohertz. There are also some additional tests in the Part 0 standard that are not part of the Part 7 and the NCS 3.22 standards. Some of the measurements we'll cover today, so I'm just going to give the names of these on this slide, and we'll talk about them more in detail in upcoming slides. So we have the OSPL 90 frequency response, the full-on gain frequency response, basic frequency response, total harmonic distortion, equivalent input noise, battery current, steady state input-output, attack and release, and intermodulation distortion, and finally the SPL-IV curve. So let's look at some of the details of these measurements. First, we have the OSPL 90. This is an abbreviation for output sound pressure level for an input acoustic level of 90 dB SPL. So most of these involve measuring the sound pressure level in the coupler. In this case, the input SPL is 90 dB SPL, as the name implies. The gain of the device is set to full-on gain, and the frequency range is 200 hertz to 5 kilohertz for the production test standards, and 200 hertz to 8 kilohertz for the R&D standard, the Part 0 standard. The results are the OSPL 90 curve, which looks like this for the hearing aid I'm going to be demonstrating today. And some of the metrics of interest here, we have the maximum OSPL 90, so we simply pick off the maximum value of the curve at whatever frequency it occurs at. And next we have the HFA OSPL 90. Now HFA stands for high frequency average, and to compute this we simply take the level or the gain at three specified frequencies. Those are 1.0, 1.6, and 2.5 kilohertz. We take the level or gain at those three frequencies, simply average the decibel values, and that's called the HFA gain or the HFA level for high frequency average. The full-on gain, or FOG, sometimes called FOG 50. Here the input level is 50 dBSPL. The gain is at full-on gain, of course. The same frequency range as previously. And here we're going to measure the gain curve, as shown here. And one of the important metrics is the high frequency average full-on gain, or HFA FOG. Now, one of the metrics called out here is the reference test setting, or RTS. In this case, we're targeting a certain gain level with an input level of 60 dBSPL. We want to adjust the gain of the hearing aid such that the HFA gain, the gain at the frequencies of 1, 1.6, and 2.5 kilohertz, is equal to the HFA OSPL 90 minus 77 dB. Now the result here is the RTS, or reference test setting, and the gain at RTS is called the reference test gain. Now for modern digital hearing aids, this RTS value can be set programmatically. Typically you would have a programmer connected to the hearing aid, with tiny little cables, or sometimes over Bluetooth, and you would send a command to the device to tell it to set itself to reference test setting. For analog hearing aids, it's a kind of a iterative process where you have to adjust the gain of the hearing aid, measure the HFA gain, and compute the HFA OSPL 90 minus 77 dB until you reach the target level. The frequency response involves, again, measuring the sound pressure level in the coupler. In this case, the input level is at 50 dBSPL. The gain of the hearing aid is set to the reference test setting. Same frequency range, and here we want to look at the frequency response curve. So we can look at this in terms of the level, as shown here, or in terms of the gain. One of the metrics here is the HFA, the high frequency average. And again, we would just take the average of the values at those three frequencies. And then the frequency range is computed by, first we draw a horizontal line at the HFA level. We draw a parallel curve 20 dB lower than the HFA level line. And where that point intersects the curve, at the low end, we designate that as F1. The high end is F2, and F1 to F2 is the frequency range of the device. Another important tolerance template that's used in both the ANSI standard and the 60118 Part 7. So this is based on the specified response curve for the model, and you construct limits that are in two frequency ranges. So we have a lower frequency range here from it's 1.25 times F1, or 200 hertz, whichever is higher, up until 2 kilohertz, shown here. And then the upper frequency range is from 2 kilohertz to 0.8 times F2, or 4 kilohertz, whichever is lower. So in the upper frequency range, the limits are plus or minus 6 dB as shown here, and in the lower range, they're plus or minus 4 dB. Now, the way this is specified in the standards, these were written many years ago when people used transparencies, and the idea was you would draw the limits on a transparency at the same scale as your measured curve. You would then put the transparency over top of the measured curve, adjust it vertically until the measured curve is centered within the limits. And they also allow you to adjust the curve horizontally in frequency, up or down, by as much as 10%. And I believe the reason for that is with behind the ear hearing aids, as we'll see, there's a plastic tube used to convey the sound from the hearing aid to the coupler. And the length of that tube can vary, which can cause these resonances to shift slightly up or down in frequency. So I think the standards are allowing you to adjust for that frequency shift caused by the length of the tubing. Next, we have the harmonic distortion. So here we're simply measuring the total harmonic distortion in the coupler. The gain of the device is set to the reference test setting, and there are 3 or 4 frequencies and levels specified at which to measure this. So we simply generate a sine wave at the specified frequency and level and measure the total harmonic distortion in %. Another metric is the equivalent input noise. So here, the input signal to the hearing aid is off. The gain is set to the reference test setting. The frequency bandwidth of the measurement is from 200 Hertz to 5 kilohertz. And first we measure L0. That's the sound pressure level in the coupler, basically the noise level in the coupler with no input. And we calculate the equivalent input noise as L0 minus the HFA gain at 50 dBSPL. Another important metric is the battery current. So this is intended to give us an idea of how much current does the battery draw as it's used for normal working purposes. It's important because these devices are battery powered, and we want it to be able to work throughout the day for users. So in this case, the input level to the hearing aid is 65 dBSPL. The gain is at the reference test setting. We're generating a frequency of 1 kilohertz, and we measure the current drawn by the battery. This measurement is called steady state input-output, and for those of us involved in more conventional audio tests, we would call it a stepped level sweep. So this involves setting the hearing aid to a gain of reference test setting. We generate a sine signal at 1 or more of these frequencies, one at a time, 250, 500, 1 kilohertz, 2 kilohertz, or 4 kilohertz. We step the level in 5 dB steps from 50 to 90 dBSPL, and we measure the input-output curve as shown here. So for hearing aids with automatic gain control, you can see that we have a linear response from about 50 to maybe 57 dBSPL, kind of a straight line, and then it begins to roll off as the automatic gain control circuit cuts in. Another metric for hearing aids with automatic gain control is called attack and release. So here, again, we're generating a sine signal, any of the 4 frequencies indicated, 250, 500, 1K, or 2K. And we generate a sine signal. We abruptly increase the level from 55 dBSPL to 90 dBSPL. That's the input signal. And we look at the output of the hearing aid, and we monitor the output level, the envelope of the signal, and we measure the amount of time that it takes the signal to settle within plus or minus 3 dB of its final level here. Similarly, for the release, we step the input to the hearing aid from 90 down to 55 abruptly, and we measure the release time as the amount of time it takes for the level envelope to settle within plus or minus 4 dB of its final value. Some other metrics around intermodulation distortion. So ANSI S3.22 calls it difference frequency distortion. And here we're generating 2 sine signals that are of equal amplitude, but they're different in frequency by 125 Hertz. Now in the next slide, we'll show the IEC version of this. It's very similar. One thing that's different: in the ANSI standard, F1 is the higher of the 2 frequencies. In the IEC standard, F2 is the higher, but they're both difference frequency of 125 Hertz, which is important. Another difference between the two, the ANSI standard has 3 of these distortion products. So these occur at many frequencies, but the ANSI standard calls out measurements at F1 minus F2, 2F1 minus F2, and 2F2 minus F1. And the sum of those distortion products is expressed as a ratio of the overall signal, and the result is to plot the total difference frequency distortion versus frequency. So as you can see here, we have a measurement called ANSI S3.22 IMD frequency sweep, and this is a brand new measurement that we've just added to the APX software as of version 6.0.1. which is the latest version currently available on our website. Now, as I mentioned, there's an IEC 60118 Part 0 version of this. It's called intermodulation distortion, but it's essentially the same thing. The level is slightly different. The two signs are at 61 dBSPL instead of 62. And same difference frequency, but in this case, F2 is the higher of the two frequencies. And this one only has two distortion products, F2 minus F1 and 2F1 minus F2. And in this case, we want to plot the total difference frequency distortion versus F2. And just like for the ANSI, we've added a separate measurement here in sequence mode called IEC 60118-0 IMD frequency sweep. So if you want to do these measurements, you simply add one of them, one or the other, to your signal path and set it up, and it does the measurement, provides the result. Now this measurement, SPL-IV, and that stands for sound pressure level in a vertical magnetic field. So this is for hearing aids that are equipped with a telecoil. And in this case, we are still measuring the sound pressure level in the coupler with the gain at the reference test setting, but instead of generating an acoustic signal with a loudspeaker, we're generating current inside a loop, which creates a magnetic field that the hearing aid is exposed to. So the audio is transmitted over this magnetic field instead of acoustically through the air. Now the loop current required in the standard is 31.6 milliamps per meter, and the amount of current depends on the length of the loop. And in the test box that I'm using today, that corresponds to a current of 7.9 milliamps. This is a sinusoidal signal, and it's swept from 200 hertz to 8 kilohertz, and you produce a graph of level versus frequency as shown here. Now in this case, I'm using a measurement in Apex called the bandpass level sweep, and that's a stepped sine sweep, but instead of looking at the wideband level, it has a very narrow bandpass filter. We've set the width of the filter to the narrowest possible setting called window width, and this is based on FFT analysis to produce the narrowest bandpass filter possible. All right, so let's talk about the equipment requirements a little bit. First of all, we need an acoustic test chamber or a test box to, this isolates the measurement from the ambient noise. It also has a built-in loudspeaker, in some cases a loop to test the telecoil, and it can convey the power to the hearing aid. We also need a measurement microphone. This is very important, of course. A 2cc coupler. So this is specified by both of the production test standards. And for the R&D standard, the Part 0, you have the option of using an ear simulator if you prefer. We also need a sound level calibrator, and we'll talk about that in a minute. Dummy microphone, again, we'll talk about that in one of the upcoming slides. And finally, we need an audio analyzer, and some of the accessories to go with the audio analyzer include a power amplifier to drive the loudspeaker. We need a power amplifier to drive the telecoil loop. We need a microphone power module to provide power to the microphone preamplifier and any signal conditioning. And then a battery simulator to supply power to the hearing aid and also to measure the current drawn by the hearing aid battery, or drawn from the battery rather. Now the one of the most popular sound test boxes is this TBS-25 sound test chamber made by a Danish company called Interacoustics. I think the same unit is sold by Brüel & Kjær under, I think they just buy it from Interacoustics and put their own model number and their own paint color. But it's one of the most popular chambers for hearing aid production test. It offers about 45 dB of noise isolation. It's specified to be anechoic at frequencies of 500 hertz and greater. And it has a very nice loudspeaker built in that has a smooth response from about 50 hertz to 8 kilohertz. And it has, it's very close to having a flat response. It's about plus or minus 3 dB from flatness over that range, which is quite good for a loudspeaker, actually. It also has a built-in loop for telecoil measurements, And there's a convenient patch panel in the front of the box. You can't see it in the picture here, but you can make connections to the patch panel inside the box, and there's a corresponding patch panel on the back of the box through which you can route connections to the microphone, for example, and the battery supply and so on. I've made a note here that the working surface area of this box is quite small. It's less than 6 by 6 inches or 15 by 15 centimeters. And that means you can't fit a lot in here. But luckily, hearing aids are quite small, so they do fit. Now, for a measurement microphone, you're required to have a pressure capsule, pressure response microphone for use with the 2cc coupler. And of course, the microphone needs a preamplifier. And our sister company, Grass, has a very nice offering here. It's the Grass 26CK, very short 1/2 inch CCP preamplifier. That's shown in the picture here with the microphone capsule attached to the preamp. So as you can see, I just put a ruler in the picture, and the total length of the preamp and microphone combined is about 37 millimeters. Nice and small, which is great for use in that chamber, which has limited space. This is the dummy microphone that we sell, and as you can see, that's about the same size and the same volume as the microphone and preamplifier combined. We'll talk about that in an upcoming slide. And now what I'm showing here is the 26CK preamplifier and the 40AO capsule purchased as separate components. These are also offered from Grass as a system and a microphone system. They're calibrated as a unit and programmed with TEDS, the Transducer Electronic Data Sheet. And the straight version here has the part number 46AO-S2. There's also a right angle version called 46AO-S3. And this one, I don't have a picture of it, but I do have a drawing, and this shows, you can see the preamplifier. There's a built-in right angle adapter, and then we have the microphone capsule. So this is convenient if you want to orient the capsule at 90 degrees to the cable protruding from the preamplifier. Now there's a 2cc coupler required for the production test, hearing aid tests. And this is specified by standards ANSI S3.7 and part 5 of the IEC 60118-5 series. And Grass makes a nice coupler that meets both of these standards. So these pictures are from the ANSI standard, and you can see for in-the-ear hearing aids, there's a kind of a conical opening to the inner cavity, and this would be sealed with sealing putty or blue tack, for example. And then for behind the ear hearing aids, they're oriented like this, and there's a piece of tubing, can be metal tubing or plastic tubing, that joins the output from the ear hook into the input of the coupler. So the ANSI standard refers to this as a type HA1 2cc coupler and a type HA2 on the right. And this RA0038 coupler from Grass comes in a nice kit like this. As you can see, you have the parts for the HA2, and you can also remove these parts and place the conical adapter on the coupler to turn it into an HA1. So this is all built into this nice little kit. Now, in addition to the accessories that I've shown, Grass has quite a variety of additional accessories that are available for hearing aid test. First of all, Grass is primarily a microphone manufacturer, and they have several models of pressure microphones that are available. In addition, there's this 0.4 cc coupler that's used for higher frequency measurements. This is important for testing hearing aids for children, for example. And I believe there's a new standard coming out which will adopt this as the standard for hearing aids for children, for testing those rather. There's this 2cc coupler for a 1-inch microphone if you may need to make lower level measurements or to meet a certain standard. And then with the 60118 part 0, there's the option to use ear simulators, sometimes called 711 couplers from the former standard. The current standard governing those is IEC 60318-4. And Grass offers 3 types in this package. There's the standard one, the high frequency frequency one, and the high resolution one. And of course, there's a variety of connection cables available to connect the microphone to the analyzer. Now it's also useful to have a sound level calibrator for these measurements. For one thing, all of these microphones have a nominal sensitivity, but that sensitivity varies a little bit from microphone to microphone. So we, using a sound level calibrator, we subject the microphone to a known sound pressure level at a known frequency, and we can then adjust the sensitivity in the software so that it correctly reads the right level in pascals or dBSPL. Now this 42AG from Grass is a very nice calibrator. It's one of the nicest I've ever used. It has 2 frequencies. Importantly, it works at 250 Hertz, which is necessary for ear simulators. And it also can generate a sine signal at 1 kilohertz. So that's a nice feature, as is the dual sound levels. It can generate 94 dBSPL, which is 1 Pascal, or 114 dBSPL, which is 10 Pascals. It has a built-in feedback microphone, which helps it to compensate for the any fluctuations in atmospheric pressure. And it has a nice digital display that can show the sound pressure level and the frequency as shown in the picture. You can also display the temperature, the barometric pressure, and the relative humidity. Now, the dummy microphone, I wanted to explain what that's used for. So there are 2 ways of conducting these tests. One is called the reference microphone method, and the other is the substitution method. Now with the reference method, you need 1 microphone inside the coupler, and another microphone at the test point to adjust the sound level that the hearing aid is exposed to. So you need 2 microphones, and of course you need an audio analyzer with 2 input channels. And we would love to sell you 2 microphones and a 2-channel analyzer, but you can also do these tests with a single microphone by using what's called the substitution method. So with this method, when you're calibrating the sound field, setting its level or adjusting the equalization of the speaker, you would put the reference microphone at the test point at the center of the blue circle here in front of the speaker, and you would put the dummy microphone inside the coupler. Then when you need to do the measurements, you would flip the position of those 2. So the dummy microphone is now at the test point and the reference microphone is inside the coupler. And this is designed so that the dummy microphone takes up the approximate same size and volume as the reference microphone and gives you the same sound field under both circumstances. Next, this is the analyzer that I'm using today. It's our APX 511 hearing instrument analyzer. I don't have the B series version. I have the legacy one, but it's functionally the same. It's a specialized APX model for hearing instrument test, and it has built-in accessories: a power amplifier for the loudspeaker, a power amplifier for the telecoil. That is, you specify the level for the coil in terms of amps or milliamps. It has the built-in battery simulator to power the hearing aid battery and to measure the current. And it has CCP power to power the measurement microphone. Now this uses the same APX software as our audio analyzers, used for R&D. And this allows for easy test development and troubleshooting between engineering and production. It has fast measurements, high performance, and very flexible software. Just a quick look at the rear panel of the 511. So I wanted to point out, this is one of the only audio analyzers, I think it is the only audio analyzer we sell, that does not have input-output connectors on the front panel. All of the connectors are on the back panel. The only thing on the front panel is LEDs to indicate the speaker is being used or the telecoil, that the battery power is on, and then the microphone CCP power is on. On the back panel, we have a standard BNC input for the microphone signal. And then we have this 15-pin D-sub connector, which is used to convey the output to the speaker in the test box, to the telecoil loop, and also the battery simulator. We provide this breakout cable for the 511 that works with the TBS-25. So this shows the rear patch panel I spoke of for the TBS-25 sound test chamber. And we have a 3.5 millimeter jack for the battery adapter, a 6 millimeter jack for the telecoil loop, and there are also some jacks for the reference microphone, and then a series of pin jacks for the loudspeaker. And over here on the cable, we have the 15-pin D-sub connector, which connects to the analyzer, the 2 pins to connect to the speaker jack, the telecoil loop plug, and then the plug for the battery adapter. So easy connections between the analyzer and the chamber. Now, in the demonstration I'm doing today, I'm using some plugins for the APX software. So these are software features that don't ship natively with the software, but they're available for download from our website. First up, we have the hearing aid test plugin. This adds a few derived results that are used in the hearing aid test project I'm demonstrating today. Also, we have an attack and release plugin. This adds attack and release measurements per ANSI S3.22 and IEC 60118 Part 0. And we have an octave analysis plugin. This is just adds a fractional octave analysis measurement, which is optional. It's not required for these standards, but can be useful for acoustic measurements. And these are freely available downloads from ap.com. All you have to do is register to download them. Once you've installed them, these features will show up in the APX 500 software. So I'm going to do the demo next, and I just wanted to point out, this shows the equipment. Of course, I'm using an APX 511 legacy analyzer and this Interacoustics TBS-25 test box. I'll be testing an analog hearing aid, and the reason I'm doing that is it's a very simple device. It doesn't require that I have a programmer connected to program the hearing aid or to upload any firmware. I simply turn it on and it works. So it's quite useful for demos in that respect. And then also on the right here, I'm showing that we have a tech note that you can download from our website. This describes the setup and the testing in detail. And we also have copies of the project file that I'll be using today for the APX 511. And then we have variations of the project file that can be used with any other APX audio analyzer, we have an accessory device called the 1701, as well as you can use an external power amplifier and so on. So that's available, and the demo that I'm going to do today is basically running through the tests that are in the projects that are delivered with this tech note. All right, so I'm just going to kick out of the presentation here and load our APX software. It's just running in the background. Now, right now, it's connected to the APX 511. And I've loaded the default project. The default project, just like any other APX analyzer, includes one signal path and a series of basic measurements. Now here, just wanted to show that the connections are a little bit different for the 511. Instead of analog unbalanced and balanced and so on, we have connections of speaker and telecoil on the output side. Here for the speaker, if we choose the settings, we have the opportunity to turn the battery voltage on. We would set the voltage of the hearing aid battery, typically 1.3 volts, for example, and turn the battery on or off. And then on the input side, the connections are microphone, battery voltage, battery current, speaker voltage, telecoil current, and microphone bias voltage or CCP voltage. Now, some of these are for diagnostic purposes, and the ones we mostly use are the microphone and the battery voltage. But for example, if you wanted to measure the telecoil current, you could change that to your input connector. So just to quickly demonstrate this, when you fire up the software and you're connected, you get a warning sign here that nothing is calibrated, because we need to calibrate the microphone and the speaker before we do any measurements. But just to illustrate, I'll just quickly turn on the microphone power. You can see here in the FFT display that it's responding to my speech, picking up the signal from my voice. And if I wanted to generate a signal here, even though nothing's calibrated, I'll just kick on the generator. You might hear that tone in the background, and you can see a nice FFT signal at 1 kilohertz. So rather than stumble through setting everything up and taking everyone's time, I'm just going to load a project file here. So it's in my list of recent projects. And this will run through the tests that we've talked about today in the presentation. So the APX software is organized as a navigator here. It's kind of a tree-like structure. At the very top of the root of the tree, we have the project file, and then we have a series of signal paths. And signal paths are where we configure inputs and outputs, and inside each signal path there are measurements. Now, you may notice that there are a series of checked boxes here, and the navigator is actually a sequencer. And when I hit this play button or run sequence button, it will step through and execute all of the checked boxes. So any measurements that are checked will be executed. And inside here, there are some sequence steps that also put up prompts and so on. And any of those that are checked will be executed as well. Now we have the ability to define multiple sequences, and I've defined 2 sequences in my project. So you can see here, this one is called calibrate, and it has a few checked boxes. And if I switch over to the test DUT sequence, test device under test, you can see many more checked boxes, but just different ones. So a sequence in the APX software is really just a collection of these checked boxes. So first I'm going to do the calibration sequence. I select it in the sequence control and just hit the run sequence button. First up, I get a prompt to calibrate the microphone. So the prompt says insert the microphone in the calibrator, set the level to 94 dB and switch it on. So following the instructions, I insert the microphone in the calibrator, turn the calibrator on. You can see a nice sharp peak in the FFT at 1 kilohertz here. And I did this webinar earlier this morning and calibrated the microphone, and it's still reading 94.02 or so dBSPL. So we won't see a lot of change here, but it might get it slightly closer to the specified sensitivity, the measured sensitivity rather, of 11.8 millivolts per Pascal. So let me click OK. You'll see the level change to 94, closer to 94.0. And then I get an instruction to place the hearing instrument at the test point, put the microphone at the leveling position as shown in the picture. And so I have the pressure mic oriented at 90 degrees to the sound field. I have to put the dummy microphone inside the 2cc coupler as shown. This is configured as an HA2 coupler in this case. And let's see, ensure that the hearing aid is switched off. And then I'll close the chamber. You can see the ambient noise go down quite a bit. I click OK to proceed. And now it's regulating the sound level to 80 dBSPL at 1 frequency. Next, we're going to use a chirp signal to measure the frequency response of the loudspeaker, as shown. And in the next step, we've equalized the sound test chamber. So here, I've set the level to 90 dBSPL, and you can see here the level at the test point is pretty flat versus frequency from 100 hertz to 8 kilohertz. I can also look at this relative level result with limits on it, and you can see that well within the limits. And this final result shows the deviation from flatness over that entire frequency range from 100 to 8K. It's 0 plus or minus 0.4 dB. So that's pretty good. Could do a little better if we tried, but good enough for this demonstration. Yeah, so what we've done here is we've measured the frequency response of the device. So this is a relative level curve relative to 1 kilohertz. And you can see here the deviation from flatness without any EQ was about plus or minus 2.3 dB, 2.4. So what we've done essentially using sequence step is we've exported this curve, then imported it to the second signal path, inverted it, and applied that as an equalization to the loudspeaker. So at this point, the chamber is calibrated over that frequency range, and we're ready to test. I'll switch over to the test DUT sequence and just hit the run sequence button, and we'll follow the prompt. So first, we have a prompt to enter the device ID. This would typically be the serial number. You could use a barcode scanner if you wish. I don't have one connected, so I'm just going to enter a number, 123478. Click OK to continue and follow the prompts. So first, it's measuring the ambient noise in the chamber with nothing turned on, and then the 1/3 octave ambient noise. Then it will measure the frequency response at the test point. The next prompt says to connect the battery simulator to the hearing instrument or install a battery. It's already connected, so I'll just click OK. And the next prompt says to place the hearing instrument at the test point and the microphone in the coupler. So I have to flip the position of the dummy microphone and the reference microphone. Insert the reference mic firmly in the coupler, put the dummy mic at the test point, and the next instruction is ensure that the hearing aid is switched to acoustic mode and set the gain to full on gain. So this is an analog hearing aid. I'll just crank up the volume control to full on gain, and the hearing aid is now in acoustic mode. And as you can see, I'm getting a kind of a noise spectrum that follows the shape of the hearing aid curve with no signal being generated. So I click OK to continue with the test here. We measured OSPL 90 with a chirp. Now we're measuring the full on gain curve. I believe this is a bandpass frequency sweep. And in the background there, you can see we're measuring the ISO R40 or 1/12th octave frequencies. Next, the basic frequency response curve. Have a prompt here to set the hearing instrument to the reference test setting. So this analog hearing aid, I'm just going to adjust its volume control. As I mentioned, with a digital hearing aid, you would adjust it programmatically to reference test setting. Close the chamber and click OK to continue. And here we're measuring the basic frequency response, again using I believe it's a bandpass frequency sweep with the window width bandpass filter. These are the ANSI limits. I'll try to remember to come back to those, but someone can remind me if I forget. And now we're measuring the THD at the 4 different frequencies. First 800 Hertz, 1.6 kilohertz. We did 500 already, and finally 3.2 kilohertz. This is the HFA at 50 dB SPL and the equivalent input noise. This test is the steady state input output. Then the attack and release measurement. And now we're doing the IMD frequency sweep according to IEC 60118 part 0. I mentioned the ANSI one is very similar. So I have one in the project here, but I've disabled it to take less time because it's basically the same measurement, slightly different levels. And next we're doing the battery current. So we'll measure the battery current 1.3 milliamps. And now we're doing a telecoil measurement. So we have a prompt. It's a new signal path for the telecoil measurement. We're driving the telecoil loop. And the prompt says to place the hearing instrument at the test point, at the point of maximum magnetic field strength with the microphone and the coupler. So for these test boxes, there could be variation from box to box as to where the maximum magnetic field is generated. And this advises you to choose the maximum point. I'm just going to leave the hearing aid where it is for this demonstration, but I do have to switch it from acoustic mode to telecoil mode, and also have a prompt to set it to the reference test gain, which it's still at the reference test gain. So I'll just close the chamber. And I just wanted to point out here in the FFT, you can see a lot of discrete components. And this telecoil mode of the hearing aid is much noisier than the acoustic input mode. So that's why we see all the spikes in the FFT spectrum. All right, so let's go ahead and click OK to proceed. And now we're measuring the SPLIV frequency response. Again, using the bandpass frequency sweep measurement. Bit of a noisier curve because it's just the nature of the telecoil. Get a prompt to set the hearing instrument to full on gain. So I'll just crank up the volume control and close the chamber again for noise isolation. And it's measuring, now it's generating a sequence report. So at the very end of the sequencer, there's a node called report, which is checked in this project file, which means it generates and displays a report. And you can see we get a nice 37-page report here. A lot of detail. We have the device ID that I entered, 123478. First, we get a summary of the measurements, all of the measurements, and an indication of whether or not it passed the limits. Then we have the instrument ID of the APX analyzer, so its serial number, the date it was calibrated, and the version of the software we're using. And then for each signal path, we get a record of all of the signal path settings, including the microphone sensitivity, for example. And then for each measurement, list of the settings for the measurement and the metrics, such as the ambient noise level, 28 dBSPL, the octave noise level, the A-weighted noise level, and so on. Yeah, it's a very, very complete display of all of the results that we measured. So basically, any result that is checked in the navigator will end up as a result in the report. So that's a very quick overview of the project. As I mentioned, these projects are available for download for you to try out if you wish. And with that, I'm just going to switch back to the presentation, and we can see if there are any questions to answer.
All right, so ladies and gentlemen, as a reminder, you can submit your questions via the chat function on your screen. While we wait to see if any questions come through, I'll take a moment to just tell you a little bit about some resources that are available to you. So if you go to our website, ap.com, we have a myriad of resources available for you. Joe mentioned a tech note regarding hearing aid audio test. That is available on ap.com. Along with, we have other application notes, white papers, data sheets, more that are available for your use. And also, you can visit the AP blog, www.ap.com/blog, and we publish content there regularly. Joe is actually a regular contributor to the blog, so be sure to check that out as well. Let's see, Joe, I do not have any questions coming through, but if someone thinks of something and you have a question for Joe that comes to your mind later today, feel free to reach out to us at techsupport@ap.com, and we would be happy to help you out. So with that, Joe, I think we can go ahead and wrap this up.
All right, well, great. Thanks for your help today, Paige, and thank you to everyone for attending the webinar.
Thank you, Joe. Take care, everybody.